Hello everyone, today I'd like to introduce a freshly published revolutionary paper on transformers. The authors include Kaiming and LeCun, and the main contribution of this paper is transforming the normalization layer in transformers into a dynamic tank layer. Dynamic tank is a very simple function, you can see it here. The updated transformer architecture compared to traditional transformers that use normalization either maintains the same performance or sees a slight improvement, and however, its computational efficiency is significantly enhanced because it no longer needs to compute the mean and variance. The change is illustrated in this diagram. Originally, there was a layer norm with normalization followed by a scale and shift. Now it's replaced with a dynamic tank, which is essentially a tank function with a parameter alpha followed by a scale and shift. Let's dive into what normalization looks like in detail. So its input is x, and it goes through a normalization process, subtract the mean of x and divide it by its standard deviation. Here a small constant epsilon is added in the denominator to prevent deviation by 0. And after the process, the value inside the parenthesis has a mean of 0 and the variance of 1, meaning the standard deviation is also 1. Then it undergoes scaling with gamma parameter either to amplify or shrink it, followed by a beta parameter to adjust the mean. This is the normalization for x. Different normalization methods vary in how they calculate the mean and variance. For example, batch normalization, the earliest normalization method, computes the mean and variance for each feature across the entire batch. Later, layer normalization, commonly used in transformers, calculates the mean and variance across different features within the same sample or vector. Another widely used method, RMS normalization, is similar to layer normalization, but skips subtracting the mean and doesn't use beta for shifting, and it only performs scaling. So why is normalization so widely used in neural networks, and why is it effective? Batch normalization was the first paper to propose that, and it says it addresses the internal covariate shift problem. So that means during training, without normalization, the output distribution of each layer shifts as the parameter values update. This means the input to the next layer, which is the output of the previous layer, keeps changing, which makes training unstable. And with normalization, the mean and variance of each layer's input became stable, fixed at a mean of 0 and a variance of 1, making training more stable and easier to converge. This was the original idea behind normalization. Later, Jingjing Xu from Peking University published a paper titled Understanding and Improving Layer Normalization, which won the Best Paper award at ACL that year, and she proposed a new norm called ADA norm and studied why layer normalization works. And she argued that the real reason isn't to solve the internal covariate shift problem, but rather a recentering and rescaling of gradients during backpropagation. So this keeps the gradients in an optimal range, not too large, not too small, with a reasonable mean. And now let's look at the paper we are talking about today. The authors first observed the relation between the input and output of normalization across 3 different neural networks. First is vision transformer, and the different plots correspond to different layers, like layer 5, 15, 20, and 25. The middle one is wave 2 vec. It's a sound-related model, and the bottom one is a diffusion transformer. These are all observed from low to high layers, and they discovered an interesting phenomenon. The input-output relation in lower layers is closer to linear, and the plot up here might not look at it, but it's actually because it's a superposition of multiple linear relations. Each layer has multiple channels. So the input-output relations of those channels are overlaid. And as you move to higher layers, the relationship becomes less linear and more S-shaped, resembling a sigmoid or a tank function. The difference between sigmoid and tank is that sigmoid ranges from 0 to 1, while tank ranges from -1 to 1. And let's zoom in on the vision transformer again. Since each layer has multiple channels, they use different colors to represent them. For example, at layer 15, the purple line represents one channel with a linear relationship, and the yellow line is another channel, also linear. And in higher layers, each channel shifts towards an S-shaped relationship. Additionally, the input distribution varies across different layers. Some range from -100 to 0, and while others in a smaller range. Next, they explain why they believe tank can replace normalization. So the tank function is overall S-shaped, but in its middle region, say from -0.5 to 0.5 on the x-axis, it's nearly linear. So I wrote some code to plot this myself. Here is a standard tank function from -3 to 3, and it's S-shaped. Beyond -3 or 3, it saturates to -1 or 1. If you zoom in from 0.5 to 0.5, you will see it's almost a straight line, a linear region. Now, if we scale, which is like dividing x by 4 or times by 0.25, it stretches the x-axis. So what was originally an S-shape from -3 to 3 now spans from -12 to 12, because 12 times 0.25 is 3. The linear region also expands from -0.5 to 0.5. Now it's -2 to 2. So whether it's an S-shape or a linear relationship, tank can modulate. However, since the input-output values differ across channels or layers, we need this alpha to scale x and fit the data accordingly. That's the core idea. How do they initialize those parameters? Simply get gamma to 1 for no scaling effect at the beginning and beta to 0 for no shifting effect. Then let the model learn how to scale and shift. As for the crucial alpha, they generally initialize it to 0.5. But the authors also found better values for specific cases. So in this section, you can see that for different model architectures, like varying vector width and depth, there are optimal initial alpha values for both the attention layer and the FFN layer. And you can use the empirical findings to initialize alpha optimally. Finally, let's talk about their experimental results. This model performs on par with or slightly better than models with layer normalization or RMS normalization across different datasets. However, in terms of computational efficiency, they found that dynamic tank significantly boosts efficiency because it reduces computational time by a large percentage. And this shows it's a more efficient function than normalization, excelling in both performance and efficiency. They also tested whether removing alpha works and found that keeping alpha outperforms both than removing it or using a sigmoid function. That's about it. Thank you, everyone.